Welcome to Unit 8, Lesson 3, Rational and Irrational Numbers. Today we'll be introduced to irrational numbers and kind of talk about the difference between the two of them. Before we get started with that, though, let's review a little bit of what we already know. 3.1, Algebra Talk, Positive Solutions. We're supposed to find a positive solution for each of these equations. Number one, x squared is equal to 36. We also see x squared for each of the other three. And what we want to do is be thinking about what number can I multiply by itself to be equal to 36. Now you may already have an idea of this, and hopefully if you know your perfect squares, you already know pretty quickly some of these pieces for finding out what the opposite of a squared value is. When we see something to the second power, we need to be thinking about the inverse of x squared would be the square root of whatever that value is. So we need to be thinking about going in that opposite direction and taking that x squared. We see that the opposite value happens. So when we take the square root of 36, when we talk about just the positive solution, we understand that x squared is equal to the square root of 36, which is 6 times 6. So we know that x is equal to 6. As you get into advanced levels of math, you would also find out, or you'd also be expected to know, that negative 6 times negative 6 is also 36. So technically speaking, when you get up in those higher levels of math, you could say x is equal to a positive or a negative 6. Something else that we can, or on the next one that we see with that, is a fraction. And as we get into the fractional value, we understand that both the numerator and the denominator are separate values, and so we need to treat them as such. What we would recognize from this is that we would take the square root of 9 and the square root of 4, and we see that that value is x squared is equal to, I forgot to do this, is equal to 9/4, which would come out to a value of x, which is equal to, or maybe we should actually look at it like this, 3 times 3 divided by 2 times 2. And we know that the square root of 9 is 3 and the square root of 4 is 2. And so we see x is equal to 3/2. I won't go through all those steps for the rest of them, just for the sake of time. When we talk about x squared, we talk about that being equal to the square root of, I just said I wasn't going to do it in here, and I'm trying to do it again. Square root of 1 divided by 4, which would be 1 times 1 over 2 times 2. And so we can see that x is equal to 1/2. And then the final one, we would see that the square root of 49 is 7, and the square root of 25 is 5. And you see, just as we get going, here's the steps, long, drawn out, down to just the simplified version. For this next one, we see that we can draw we're supposed to draw 3 different squares of different size with vertices aligned to the vertices of the grid. For each square, label the area, label the side length, write an equation that shows the relationship between the side lengths and the area. So the key thing is this, is that we have to have 3 squares of different sizes with vertices aligned to the vertices of the grid. And so when we're talking about these vertices that are already given here, what we might do is we might go ahead and divide right here, but that's no longer a square. And so we need to continue to break up these squares until we see more squares that are inside of there. And so now this one, to be able to consider that as 3 squares of different sizes, we have different squares that are built inside of here now. And so we want to take these values, and we can see that we have 1, 2, 3, 4 by 4. And we see that this is a 16 square units. Let's just leave this one as it is. We see a 2 by 2. And this one gives us a value of 4 square units. And then for these other ones, perhaps we want to call this one a 1/2 and a 1/2. So we take the whole side and we look at it as a 1/2 by a 1/2. And we can recognize this one as an area of a 1 by 1. So each of these values in here would be a quarter of that square unit. Just as right here, we would see this is 1, 1, 1, and 1. So this one right here would have a total area of just 1 square unit. And you kind of get the idea. The equations that show these ones, we would see x squared is equal to 16. This one would be x squared is equal to 4. And this would be x squared is equal to 1. Mostly because we see that these sides are 1 by 1, right? On to the next part, looking for a solution. Are any of these numbers a solution to the equation x squared equals 2? Explain your reasoning. We have the number 1. If we talk about this as x squared is equal to 2, we understand that this number right out here is equal to x. So each of these down here are x. And so we have to take into consideration this piece of saying is 1 times 1 equal to 2. This will be a no. 1 times 1 equals 1. And then the next question is 1/2 times 1/2 equal to 2. And that'll also be a no, because 1/2 times 1/2 is equal to 1/4, not 2. And we see that we could continue going on through this pattern, and the whole idea is that we're substituting that value for x to see is there a way that we can find that value. Now you'll notice I have a question mark above the equal sign. That's just simply stating, is this a true statement? 3 halves times 3 halves is 9/4, which is not equal to 2. And we do 7/5 as x, so 7/5 squared, is that equal to 2? And we see that that's a no as well. This is 49/25, which is not 2. So they're close, but they're not equal to 2, at least these two right here. As we go going through this, what we recognize with this is that there's actually not a square root of 2. 2 is not a perfect square. There are no two factors that can be multiplied together. They're the same number to equal 2. When we talk about a rational number, it's a rational number is a fraction or its opposite, meaning it's reciprocal, but any number equivalent to the fraction or its opposite. So when we talk about finding some more rational numbers that are close to the square root of 2, we can come up with a lot of different things that are out here. We could talk about 99/50ths. We could go with 199/200ths. Whoops, just kidding, 100ths. Basically, what we can look at is we can find any fraction that would come up to something that's really, really close to 2, but it won't quite work. I mean, I could even say 201/100ths, and these are all fractions, and so they're all rational, but they don't come up to the value of 2. Can you find any rational number that's exactly the square root of 2? And the answer for that is no. When we look at the square root of 2, there is not one single number that can be multiplied by itself to equal 2. So that's what we're looking at with these when we talk about rational versus irrational numbers. This is the case for most numbers that are taken to a square root. We could talk about square root of 3, square root of 5, square root of 6, square root of 7, square root of 8, square root of 10. And you'll see whoops, I wrote 9 there. You'll see that each of these numbers, we skipped over square root 4, square root 9. We can start, as we build this up, we'll start to understand those pieces. If you'd like to go ahead and get into the Are You Ready for More, please do. But you can play with this with the calculator and make some predictions and some work with those pieces. Going into the summary, let's see if this clears some things up. In an earlier activity, we learned that square root notation is used to write the length of a side length of a square given its area. For example, when we had a square whose area is 2 square units has a side length of square root 2 units, which means this. Square root 2 times square root 2 equals 2. The reason for that is because square root 2 times the square root 2 can be thought of as the square root of 2 times 2, which is the same thing as the square root of 4. And so we can understand then that all of these would be equal to 2. A square whose area is 25 square units has a side length of the square root of 25 units, which means square root 25 times square root 25 equals 25. Or we can also think about it like this, is square root 25 times square root 25 is square root 625, which equals 25. But we also know that 5 times 5 is 25, and we know that square root 25 is 5. So square root 25 is an example of a rational number. A rational number is a fraction or its opposite. Remember that a fraction of a over b is a point where a number is found on a number line. It is divided the segments from 0 to 1. So it's going to be found somewhere in between those values. Something I missed here, this would be the same thing as saying 5 times 5 is equal to 25. We have to understand that when we take the square root of something, we have to understand first off what those values mean and how those values work. One way that we can look at this, because fractions are ratios and are closely related ideas, fractions and their opposites are called rational numbers. Notice that ratio is built inside of that value. So some examples of rational numbers are fractions like 7/4. 0 is rational. 6/3, 2/10, -1/3, -5, the square root of 9. The negative square root or the opposite square root of 6, the opposite of the square root of 16 divided by the square root of 100. And we can look at these examples as fractions or its opposites. We can think, okay, well, 7/4 is just simply 7/4 is 0. 6 divided by 3 is 2. 2/10. The opposite meaning that it could be a positive value. This one might throw you off just a little bit, but the opposite of square root of 16 divided by square root of 100 is going to be 4/10, which does break down to a smaller value. So the idea is that we can actually get a measurable, exact value. With an irrational number, we can't do that. It's a number that is not a fraction or its opposite, meaning it does not have a negative value. It does not have an exact positive value. The square root of 2 is definitely a great example of that. We can also get into other examples such as square root of 17, 65, 10, the opposite square root of 3, square root of 5 divided by 2. We find out the idea of an irrational number. One other thought with that is an irrational number. The reason that when it can't be written as a fraction, a couple things happen. The number never ends. The number never has a repeating pattern. It's kind of why pi is such a fascinating number, because we don't know what its exact value is. So there you go. There's your lesson for today. Working through rational and irrational, understanding the difference between the two, that rational numbers can always be written as fractions or their opposite, meaning into a negative value, or an irrational numbers can't be written as a fraction. That is, they can't be written as a fraction because we just can't find their exact number. Putting them on a number line, we can get close, but we can't find the exact value. So that's it for today. Let me know if you have questions about it. Have a great day.